Okay.
We start in 1 minute, right?
Yes.
Yeah, some of them are my students.
So how many students have you got?
Yeah. So I teach a course on big data and science.
Okay.
So we go through like some proofs and some techniques and then read papers and do projects for a semester.
That's great.
Yeah.
That's great.
Hey, good. Let's start. So welcome everyone to our second seminar of this seminar series, Machine Learning in Finance. And today it's a pleasure to have Wang from University of Groningen. And Weining will present her paper about beta sorted portfolios. So Weining, you have approximately 45-50 minutes to present, and then we will have discussion. Would you prefer to take some questions in between if there will be some in the chat, or will
I
we
don't mind.
postpone them?
Yes,
Okay, you don't
I'm
mind.
happy
So
to take questions in between.
Great. So maybe if there will be something pressing, then we will interrupt you in the meanwhile. Okay, so please, Weining, the floor is yours.
Great. Thanks a lot for the invitation. And I'm presenting beta sorted portfolio. So because the time is tight, so let's start. So the motivation of this paper is about the constructing expected returns into factor loadings and the corresponding price of risk for interpretable factors. It's always a task for a lot of empirical finance and metrics papers. So the branch of literature working on this would be divided into unobserved pricing factors and observed pricing factors. And for observed pricing factors, typically people either do this two-pass regression, and also there is a parallel approach named as beta sorted portfolios, which is our focus today. And it's a popular approach for empirical literature, and beta sorting can be used to identify risk factors, estimate risk premium, and test the structured models of asset pricing. So it's a very simple, intuitive approach. So the first step is that we estimate the time-varying factor exposures by some regression. So it's typically taking the firm level as equity returns and regress it on some observable given risk factors. And the second step is to use this estimated regression coefficient from the first step and sort the stocks into portfolios based on the first step estimated coefficient. So it's a very popular approach in empirical work, and little work has been done to study the statistic properties of this procedure. So in this paper, we try to initiate and develop a statistical framework for studying the properties of this beta sorting procedure. In summary, we propose a econometric framework to rationalize this two-step estimator used in the literature. So we show that actually if one conduct such kind of beta sorting procedure, this model setup does not automatically impose non-arbitrage assumption, but instead the estimator coming out of this procedure can be used to test to develop a hypothesis testing for testing non-arbitrage implications. So econometrically, we cast this two-step. Okay, question.
It's from me.
Yes, great.
Yeah, I mean, one question is this. So this non-parametric estimator, two-step estimator, does it exist, or you are proposing this for the first time?
Does it? So the first step would be already studied in Ann Christensen
Okay.
in the Journal of Financial Economics literature, but their setup with time leveling is a bit different from us.
Okay.
And we will see the math, and I will mention that a bit. Yes.
Yeah, and then you're studying the both N and T being large, and this has not been done before.
Yes, and with regard to portfolio sorting, I think they have a paper. So my co-author Matthias, they with Richard and the other co-authors, they talk about characteristic portfolio. So with some given known variable, where in the first step you don't sort on beta.
Okay. Thank you.
Yeah. So indeed, we studied that the number of asset to be large and the number of time period to be large at the same time, which is a standard large and large T setup in panel regression. So in this paper, we provide conditions which implies consistency, asymptotic normality of the beta sorted portfolio estimator. And we showed that it's a bit of more challenging when we write down all the math in detail. It seems to be very simple, but there are many details going on. I guess it's true for a lot of econometrics papers. So some of the results we cannot rely exactly on existing development for non-parametric estimator. And also there are additional issue is this two-step approach is that you're balancing between the first step. So for the first step to estimate beta, you need to decide on the rolling window you would like to, so how much data or how long the time period you want to use to estimate beta. So it's a rolling window size. So translated into econometrics language, this is the balance, the bandwidth, right? So the first step, we need to decide on the bandwidth. And the second step, we need to decide on optimal number of portfolios to choose. So this in econometrics language, it's the number of the sieve dimensions. So we need to balance between these two tuning parameters in the first step and the second step. And apparently, what is optimal for the first step estimator may not be the optimal for the second step estimator in terms of bandwidth selection. And we show that the rate of convergence depend on the object of interest. It can be non-uniform, and it depends on the evaluation point of this beta. And so in addition to the literature where people typically does beta sorting, what we add on to the theorems that we can add on more precise or more narrow bands for the estimator that gives you precise inference. But in terms of preciseness, it's not like exactly say that we are better, but we are giving a sort of narrow bands in certain perspective. So I will be more clear with what I mean later. Okay, so there are many things. So it's a kind of a big project we working. So there are many things when we talk about when we do the project. So first is this new uniform inference procedure allow for uncertainty quantification. And a plain question to ask is that if one keep on doing this portfolio sorting, right, estimate beta and sort on those betas and keep on doing this, for example, high minus low investment, and would one make money in, say, like over, if you would take the average returns over a certain period, whether we're going to make money. So this kind of question can be answered by this uniform inference procedure. So I can give you a more concrete answer for that, use a statistics significance test. Okay, so we can also, so say if you are just interested in the fixed months, if you just want to fix 1 month and understand the returns, portfolio returns on this beta sorting procedure, then we can also provide some inference. Okay. And empirically, we propose a confidential risk factor that is the major, that is majorly coming from my co-author who works in the New York Fed. So the confidential risk factor, to summarize, is a measure of business credit cycle, and it's combined information from Federal Reserve Senior Loan Officer opinion survey. So they do some questionnaire to banks to measure the tightness of the borrowing. And there are some ISF manufacturer index, which is not exactly public available. So tightness of the credit, so I would say. So these factor, okay.
Again, it's me, sorry.
No, that's fine. Thank you.
I don't want to monopolize, but like one question regarding the risk factor, I think this is important. It's important to suggest something that I think that's very valuable from practice point of view. Is there like a changing weight between these two variables, or is it a fixed weight between ISM and then the SLOOS?
I think so. I think
So
it's fixed. It's like a ratio.
Okay, thank
Yeah,
you.
but this I think the first one is let's say scale invariant. So it's percentage minus percentage. That's according to the explanation from my co-author. But if you're more interested, you can raise a more questions, I guess, to him.
Thank you.
Yeah, thanks a lot. So we show that this risk factor is strongly predictive for both. So compare with those benchmark factors in the market, it's very strongly predictive for the variance of those returns, cross-sectional stock returns. Okay, so I mentioned a bit on the relationship to the literature. There are many papers talking about unobservable factors and estimated using, for example, PCA approach. And in this case, we focus majorly on those risk factors that are observable. And we are related, of course, in parallel to this Pharma Macbeth to past regressions. And there is a subset of literature allows for time-varying risk factors, as I mentioned. And our DGP shares some feature with this model, but we are not nested to, for example, this paper by Olivia Scagliet. So we are not exactly nesting their framework. Okay, so I will be more clear with the DGP. So the starting to translate what people commonly do in practice. Let me repeat the procedure again. So first is the time-varying risk factor exposure are estimated through a backward-looking weighted time series regressions of asset returns on the observed factors. So it's very important that we are doing so we only use backward-looking window. So essentially, if you translate these things in econometrics language, the kernel should be one-sided. And usually the current observation should not be included in the regression. And the second step is the estimated factors exposures based on data up to the previous period are ordered and used to group asset in portfolios. So so people ask me why we do sorting, right? So if we group stocks with similar betas, with similar levels of betas, so these portfolios kind of represent asset with similar exposures to the risk factors, and then we can sort of invest those portfolios as a representative. So the degree of return differentiation for different exposed asset is used to assess the compensation for bearing this common risk. So most frequently, so you would hear it many times, right? So people do this high minus low. And in our case, we figure out that there is, for our specific risk factor, there is a significant downward sloping. So essentially means that high beta groups tends to give your low returns, and low beta groups tends to give you high returns. And we believe that has investment implication. So importantly, we want to check if we average over time of this return differentiations, right? So we want to infer like whether we can make money, or we can infer whether the risk is priced unconditionally, whether the portfolio earns systemic excess returns. Okay, so in the long run, whether we make money. So time series of return differentiations is compared to exit risk premium estimates from the literature. Okay, so in the introduction, in the first step, we make, as I said, so verbally, we put a formula as a translation for what I said verbally, right? So notice that we do like a local constant estimator exactly because that match what people do in practice. And what people do in practice that they take a window. So typically this is, say, like 5-year rolling window, and 5 years is the most common rule of thumb in the empirical literature, which consists of roughly, if you do monthly observation, consists roughly 60 observations. So this age is 60 in that regards. And then we leave the current time period out. And this is just X is just a vector, so 1 and the vector of the factor known factors. So it's a OLS regression with a certain like number of observations over time. Well, you can complicate the things in a lot of dimensions as an econometrician. Yeah, but I think this is the most simplest thing we can deliver. Okay, so again, the key important thing is that it has to be looking back, and for econometrics purpose, right? So we exclude the current observation because in the end, with a generated error, we are just conditioning on the past information, and we don't want some correlations of the generated error appear when we do the math. Okay, so for the second step, in this step, we fix a certain time point. Say we fix a certain month, and then for the fixed certain months, we would collect all the estimated data from the beta from the first step, and then we would try to partition those estimated coefficient into 10 portfolios, say. So 10 is a rule of thumb also in the empirical literature. And so once we ordered the betas, and we also ordered the stocks, and with 10 portfolios, then we can just, sort those stocks according to the ranks of betas. So once we fix the portfolio, we can take the average returns of the stocks in some certain portfolio J, right? So the CJT is denoted as like an interval, which estimated from the values, all the statistics of betas. So the upper and lower bound of this interval is exactly the order statistics of the betas, depending on how many portfolio you select. So PJT is the J's portfolios interval. And this mathematically is so this, verbally just means that once we decide on a portfolio, we take an average of those returns within that portfolio. And so if you select, for example, the high beta group, and then this is the return for the high beta group. Okay, so in the long run, if you want to say, since we fixed T, in the long run, if you want to check the long run return, or a certain time period, say 1 year's return, you can take an average of this high portfolio over this 1 year period, right? So each time you would get such an estimator as the average return in the high beta group, and then you take the average. So this is a long run time average. Okay, so one note is that I think because each time point T you are doing a sorting, so the number of stocks or the index of stock would enter the group, enter the high beta groups would be different for each time. But for if you fix your evaluation point, or if you fix your portfolio, let's say if I'm just care about the first portfolio, the high beta portfolio, then kind of for each time I'm getting this such average return, right? So then I'm getting this over time, I'm getting this returns of the high beta group as well. And JT can be chosen differently for each time T. And again, so as I mentioned, this seems to be like a question like, what is the optimal JT? Or what is the optimal like time length we should look like for this particular procedure? So to further do some more precise math, let's go to the introductory examples from a standard textbook. So in the standard unconditional framework, so we know that the returns is summarized by alphas and betas loaded on FT, and this is a very reduced form model, and we know that the alphas and betas, depending on what factor you choose, they all need to follow specific reduced form structures, right? So in particular, if you choose F as an axis, returns alphas tends to be 0. And if you choose other factors, so it seems that there are some specific form of alphas should be given. And also, like, so when one would like to impose a non-arbitrage assumption, seems that the linear structure with respect to beta of the alpha coefficient should be there. So this is so people also like to estimate alphas and betas. People also use reduced rank regression, therefore. And with a conditional framework, it would be a little bit different. So as I say, so the time labeling is a bit different from Anna Christensen. So we see that the RIT indeed is loaded on this alpha and betas and contemporaneous factors and some idiosyncratic terms. So they are like time-varying coefficients that are measurable to the filtration in the past, so which we define. So FT is an information set at time t. And we also define some JT. So GT is a sigma field that do not include those thing varies over I. So it solely collects all the cross-sectional invariant factors information. So we need that because something is tricky with respect to the assumptions. And epsilon IT is the idiosyncratic error term. So when we try to map from the standard textbook, the conditional version, and we figure out that the second step motivate us to look at the conditional returns. So the conditional returns with a conditioning of RIT given FT minus 1 with some, so we need to assume that for factors, conditional expectation of FT minus 1 is equals to a conditional expectation of GT minus 1. So that's somewhere in our assumption in the paper. Yeah. So we are interested. So supposedly we are only interested in the conditional returns, which is only the conditional expectations of these factors, because we assume conditional FT minus 1 of this factor is the same as conditional GT minus 1. So this is the form of this mu t beta IT. And because beta IT is assumed to be measurable to FT minus 1. So it's naturally taken out. And once we do the rewriting of the model, then we have the mu t beta 1 beta IT as the function we're interested as a signal. And then we can roughly understand these things as the noise terms in a cross-sectional return. And there is something like a lag of time labeling. So in addition to the idiosyncratic term, we have some like factor term that accounts for the difference between the contemporaneous factor and the conditioning information of the factor. So we're going to work these as kind of the error terms in the cross-sectional returns, and which creates some difference in terms of asymptotics. So there's a few remarks. So say that we mentioned that these alphas and betas are supposedly to have the reduced form structure following from, what is actually your utility optimization problems. How do you assume your utility, etc. Right? So a lot of things like what do you set as your factors. So for more detailed form, you can refer to standard textbook. So in particular, the non-arbitrage assumption should be associated with some linear structures of these alphas in terms of beta. So any departure from this linear structure would be kind of saying like a departure from non-arbitrage assumption. So this is why we say that our paper can have some implication of testing non-arbitrage assumption, because testing the structure form of this mu t beta, uniform inference on this mu t beta gives us some way to infer that how do we depart from this linear structure. And for a fixed t, as we mentioned, in the error term, we have additional term here. And for fixed t, because we only have one observation for this error term, therefore, we can never learn this mu t correctly. And instead, we can only like learn this mu t plus this thing together using only the cross-sectional observations. Okay, so note that if we take the time average of this MTs, it would consist of two parts, right? So one part is the average of this conditional returns, is sort of the thing we are interested in, because the investors are kind of interested in the like the returns over conditional returns over a certain period, and then it's plus something that is so this is a martingale difference sequence by definition, and if we take the time average, then it's not surprising to expect that under certain mind assumptions, it's going to be a root t term appeared in the error term. And typically, if you do like some I, some t, and this will be the leading term in your pendulum regression because it's root t. However, if your beta is very close to 0, so this term is going to degenerate. Okay, so I'll come back to this fact later. Again, we make a little bit more complicated summarize. So we see that first we estimate the OLS, right, with this window size H. And second, we show up the order statistics of the portfolio. So this is our kind of portfolio bounds, right? So this is how you decide your portfolio. So you get all the statistic of beta, and then so according to this value of beta, we sort the stocks into it. And the second the second step, as we mentioned, is that so if you write things in the like partition regression language, the kind of quite different thing is that you have like what do you have? You have more like evaluation point, right? So this indicator function is indicating whether beta. So this is some evaluation point you decide in advance, right? Say 0. I'm interested in the average returns at level beta equals to 0. So then 0 is your interested evaluation point. And you see that whether 0, you trace whether 0 falls into a certain interval J, right? Then this will be your interested evaluation point or evaluation. This determines the evaluation like portfolio. And then you put these indicator in the together with your this is the average or the regression we saw just now, right? So if you just have those indicators, then it's equivalent to taking an average. So, and then we put together with this estimator in each portfolio with this evaluation point, and this directly gives us, say like for beta equals to 0, I find my portfolio, and then this indicator locates the corresponding averages within this vector, right? So it just gives me the return of this specific portfolio that the evaluation point find. And the grand mean estimator for a specific value of beta is then the time average of this mu t beta hat. And the high minus low would be like taking the difference of the highest beta minus the lowest beta. So taking the difference of 2 points of two critical points of this this function mu hat. So with the we actually there are various. Oh, okay, thank you.
Hi. Regarding your theorems, do you assume large JT to be fixed?
JT to be fixed. Do I allow JT to be fixed?
Yeah.
That's a good question. Yeah, I think so.
Okay, thank
But
you.
maybe if JT is not fixed, it's not that interesting. Or yeah.
Yeah.
That's a good question. I think so. Yeah. Yeah. And okay, so for the first stage estimator, we have some bounds uniformly over I and uniform over T. And we have to have some assumptions. I will go through briefly assumption a little bit. And this is not some surprising rate, right? So this characterizes the estimation error from the first stage nonparametric regression, which is controlled tightly enough to accommodate the second step estimator. And we provide results if one wants to conduct inference on these betas. Of course, we provide some central limit theorems in there. And again, one side, leave one out kernel, no look ahead bias. And then we do a kind of linearization. Okay, so these are the read conditions. Seems like I don't think we restrict J to be diverging. I think so, but kind of we're working with J tends to infinity. Yeah. Though that's a good question. Yeah, because I guess it's not, yeah. That's a good question. Well, oh, yeah, then I can answer. Because the bias. So if you want to keep J fixed, then you need to go to a parametric framework firmly assume your model is have no bias, right? So in that sense, the J has to tend to infinity. So then if this is the answer, right? So because this is a non-parametric model and we have some bias which decays with J. And if it's parametric, then you have to firmly believe in your model that the J, you have no bias. Then the bias is taken away. Yeah. Yeah, that's a difference intrinsically between non-parametric and parametric approach. Indeed, kind of we cannot allow J to still, so the theory is working, cannot allow J to be fixed in this regards, in the regards of bias, right? Okay. So essentially, if we keep J fixed, then it means that everything goes through with variance, but you have to basically say that if there's a J to be fixed, then I correctly specify my J such that there's no bias, and then the theory can be modified to that. Yes. So we have the leading term linearization, which is formed of two terms. Yeah. So the answer is no, the theory cannot work right now with J to be fixed due to the bias term. And so we have two terms. One term is the average of the idiosyncratic term. So this is usually what you do when you do what you have when you do the non-parametric regression. And we know the rate is roughly, let's say root T and what is it, root N times root J, something like that. And this one is typically faster. And the second one is the average of the factors, right? So this is the Martingale difference term. And this term is typically root T and it's typically slower. But however, it only changes when we are closing to the evaluation point of 0. So I think I guess some question like how does it perform in terms of weak betas, and also for weak betas, this term will be small, I think, and we're just sorting on noise and this type of things. So essentially, we won't been able to, okay.
Weining, you have 10-15 minutes.
Okay, great. Okay, so essentially we have two terms, and I'm kind of finished, and the bias is something we derived. Okay, and then we have two type of estimator. This is sort of an update from the previous talk in NBR. So we have a sample average conditional expected returns, which is CASR, and a population average conditional expected return, which is called PACER. And CASR represents the average expected return in observed sample. So, and this is a random object through conditioning of JT. In any sample, it reflects the realization of some economic wide state variables. And if the mu t is constant, CASR equals to PACER. So PACER represents a population average expected returns. And so this is our form. So it's a prelim of this average of mu t. And in the central limit theorem, so we figure out definitely it's going to be different, right, for the asymptotics of CASR and PACER, because if you censor at the conditional average, so you get less variance. If you censor at the long run like variance, you get a larger variance. So it turns out that the Farmer-Macbeth hate this variance, and we have some plugin version of estimator produce us a narrow bands that only gives this variance. So we will see that because this is only the conditioning version of it, and so you have less variations. So we see that there are three like three parts in the variance estimators, and this is a standard one, and then a decomposition, right, of this FT. So this sigma F is always there for CASR and PACER, and this is the FT minus the conditional mean of the FT. And then there is the variation, overall variation of mu t on the long run, like say long run steady mean, right? So if you care, like if you want to benchmark mu t on its prelim, then this one also captures additional variations. So again, let's see, this one only show up when you're interested to benchmark your object into the population mean, and which may not be the interest in a lot of cases. Okay, so the paper provides precise result with ensure consistency and asymptotic normality, and the key for result to hold is that beta is the presence of both term in standardization of variance, and to our knowledge, it is the first formal result to justify beta sort of portfolio. Okay, so we mentioned a bit on the rate of convergence. So the rate of convergence for the grand mean is affected by this term. As we mentioned, it's generally root t when you move away from beta, from 0. And then so if you take a different diff, you can get rid of this term and get the standard like a non-parametric rate, right? So instead of centering at this conditional return, you can center at the correct, right? So you can include this term, and which is the samplage of the systemic realized returns for asset with exposure beta. So it's kind of exposed risk premium. So also, like if you want to remove this inference of this term, as we mentioned, that you can take the diff in diff portfolio investment like butterfly trading strategy. Okay, so then we change a bit on this Farmer-Macbeth claim versus our previous version, is that the Farmer-Macbeth actually just exactly correspond to overstates the variance estimator for CASR, but it's precisely consistent estimator when forming confidence interval for PACER. So, and if you're interested in covering the prediction interval for CASR, it's going to overstate the variation. Okay, so therefore, the confidence interval constructed by Farmer-Macbeth and the confidence interval constructed by some plugin procedure as we proposed is different. Okay, so this is our plugin approach. Just some common remark is that we are kind of against putting a specific data generating process for FT. But however, so when estimate this conditional return for the variance, we kind of use a feasible parametric estimate. Say you can put like the AR1 model, and then you can plug in, use this parametric form. So that is different from generally, like overall, we don't put any, say, assumptions on the DGPs of FT, but only when we estimate this conditional expectation for this variance. And if this, of course, if the parametric form is correctly specified, then the plugin variance estimator is consistent. And under misspecification variance estimator, it overstates the variation. Okay, so this is our plugin. And as we mentioned, if you are interested in a prediction interval for Caesar, then you use this plugin. Okay, so for fixed T estimation inference, we also have a set of results. So after we change our draft 4 times, so we delete everything in the main text. Now with the current version of the paper on fixed T estimation, we delegate all of them in appendix. So just to say that for fixed time point, if you're interested in inference, you can only make inference on the whole object because this just have one realization, and you're never going to able to say anything statistically for mu t. And again, so we can take the diff and diff procedure, which correspond to a butterfly trait procedure, and this help us to get rid of this term. Okay. And a natural test statistic could test to say like if whether the butterfly trading strategy for a fixed month T can give you sufficient return is to consider such supreme statistics. And then you need to construct uniform confidence intervals in there, and then draw the relatively statistic conclusions. We have a uniform inference session for the paper, both for the fixed T and for the average T setup. And in our current version, I guess all this uniform like Gaussian approximation result has been delegated to the appendix as well. So just a remark, so this is kind of things for the Caesar, right? So we are centering only at the conditional mean. And then the variance is smaller. And then we can say that the supreme of this average can be approximated well by the maximum of some Gaussian process with a similar type of variance. I think it's this statement allows us to get a prediction interval for the Caesar. You can just draw quantiles from this Gaussian process, and then you will get the prediction interval that covers this average with a certain probability. Hello?
3 minutes.
Okay,
Thank
great. Oh, okay. So I can go a bit on the empirical applications as a kind of very interesting empirical application, as I said. So our factor is some measure of credit to GDP ratio. And again, so the raising of the Sloan survey and the drop of SMT represent a raising of a CCW factor, but it's associated essentially a drop of the credit to GDP. So it's tightening of the credit ratio. Okay, so we're checking whether via some prediction regression with various horizon that we're checking the prediction power of this factor. So essentially, we we run many like prediction regressions, I'll find out that the CCW factor has very strong prediction power for the cross-sectional returns compared to all the above listed, stylus factors in terms of prediction regression, and also in terms of both in terms of the in-sample R-square and auto-sample R-square. So it has very good prediction power. And okay, so then here is the theoretical correspondence, empirical correspondence of our Caesar and Payser intervals. And we see that with a plugin variance that corresponds to a prediction interval of the Caesar, it's way narrow than the Farmer-McBeth variance estimator used for the long-run benchmark. So it's kind of saying like, I guess empirical people would perform a more informative inference with narrow band. And it's just saying like, if you want to benchmark everything just in terms of the empirical average of the conditional returns, you don't want to wait until everything to benchmark to the long run return, then it's going to give you like way narrow bands. And again, we are not saying that we're better than Farmer-McBeth or the Farmer-McBeth is wrong, because this is a confidence interval and this is a prediction interval, as was stated. And we find out that we also report the pointwise inference on the time average of the expected returns. And it's strictly the same as kind of the uniform confidence bands produced. So Farmer-McBeth, in terms of confidence interval, performs wider bands, produce wider bands, and where in the plugin variance produce way narrow band. And this is just saying like, so strictly it's the average returns is going to be a downward sloping shape. And the plugin variance shows that this shape is strictly downward, and it's not like for the Farmer-McBeth any like constant line would pass through. And it's just telling us that if you sort betas according to this confidential factors that Fed provides us, it's the high beta groups in general, the high beta groups here is going to produce you strictly low return than those lower beta groups, and it's going to potentially giving you a lot of money. Yeah. So the conclusion is that we provide a comprehensive framework to study the economics and statistical properties of beta sorted portfolio. So we translate the two-step estimation algorithm into a corresponding statistic model, and we show that model has key features which are important for valid interpretation of the empirical results. And we provide a battery of results that are useful for estimation inference, including consistency, asymptotic normality, and uniform inference procedures. And we provide prediction intervals for Caesar, and we show that the commonly used Farmer-McBeth variance estimator is valid, but maybe unduly conservative. And we propose new plugin estimator to find it perform well in practice. And so empirically, we introduce a new risk factor, a kind of measure for business cycle, and show a strongly predictive of both cross-sectional returns and time series behavior stock returns. Okay, so here is something like assumptions. It's very simple, and it's, yeah, thank you.
Thanks,
Thank you.
Weining, for the talk. Perfect timing. So now we are ready to take some questions. So if you have some questions, please type them in Q&A section. So for now, we don't have any questions. Weining, maybe if you could go back to the empirical application when you had this graphs. Yes, this one. So looks to me that so I'm just wondering, very parsimonious question. Would there be empirical difference if we just, let's say, take piecewise constant, then kind of linear interval, and then again constant? So it looks that it's still a little bit maybe too flexible in this middle range.
You mean this one?
Yeah. So I just empirically, if you replace this kind of estimator, yeah, with a linear function. So
yeah,
didn't
I
you
guess
try something
relatively
like
to the Farmer-McBeth variance bands, right? So which easily goes through like a constant line. So basically it's uninformative. So essentially it says like portfolio return, like there's portfolio sorting returns in the long run does not give you any return differentiation. So that's a practical like implication. And for our case, I think and this in this narrow bands, I agree with you that maybe some region you can still draw like a constant line, but I don't think strictly you can put like a constant line.
so linear?
Across
I mean like constant, then linear in the middle, and then again constant. So
yes,
it
yes.
still seems a little bit too volatile for.
So you would say that and that's sort of reasonable for the constant region because we don't have that much observations anyhow for those two constant regions. And so those relative reformative one would be, I guess, the betas concentrated in where you have most observations and it's way linear compared to this. And this is roughly the benchmark what you can do for according to the I guess according to the literature, the Farmer-McBeth one.
Okay.
I still feel like it's more informative, but I agree with you that looks yeah, so note that for each, okay, we're just doing piecewise constant, right? So for each fixed time, it's like piecewise constant portfolio line, and you're averaging so those piecewise constant over time. So therefore, you'll say such a shape, and it's a little bit wiggly. And of course, I mean you can try like within each bin, you can run like polynomial regression. It improves the property and your estimator and the bias definitely improve. But yeah, so then it's again a little bit more detached to what people do in practice with portfolio sorting.
And is there any way to impose a kind of monotonicity in this region? Or it wouldn't make any practical sense?
So because you can, okay, so this is a time average fit. So imagine like when I do, maybe it's a good question, right? So I fit for each time a mu t, and then I have no control of I fit at each time a mu t, and I have no control about my portfolio, like for like which stock enter the portfolio and the shape of this mu t, and then I'm taking an average. So I don't know, maybe you can take those things. You can, well, if you really want to fit some monotone line in there, and I guess you can take my raw estimator here and then further do some fitting by solving some optimization procedure. But I don't know what that gives
direction
you.
of isotonic things, so where you can impose.
But isotonic regression typically comes from a regression problem, right? But this line comes from time averaging of some estimator.
Yeah,
So
I mean something similar, yeah, in that. Because I would expect that it should be, but yeah, I don't know.
Yeah. So in fact, this downward sloping does not show up always. So we tried the thing with any like many other factors, like, right? So for example, you can try inflation, you can try with something like whatever factor with like this pharma French models, right? So it's the downward sloping slope is not always there, I would say. So it's not like universally true. So even I guess probably you change different time period, you would get, say, for example, a U shape or whatever shape. So yeah, I don't know like whether indeed, I mean, it's empirical appealing that we actually use our factor and produce a very nice, you know, tight downward sloping curve and bend. And yeah. So but I kind of agree in your saying, say like it would be reasonable to think to regularize this wide curve a bit. But to regularize that, I think it's more natural to use like, you know, a little bit more advanced technique. Like, for example, for the first step to reduce bias, you can try local polynomial. For the second step, you can try like so this is kind of reducing bias techniques at the lower level than to say like impose a monotone isotonic regression technique for getting such curve. It with respect to the time average, I didn't think about it. And if you, I'm pretty sure such technique exists, you can't do that. But what does that mean in, you know, for investor financially?
This, I don't know, maybe we have some investors in the audience who
Yeah.
can who can contribute to this discussion. Yeah, so for now we don't have any questions in chat. So Mehmet, if you have some questions.
I'm good.
Okay, then Weining, thank you very much once again for this nice presentation. It's yeah, it's pretty impressive work. I hope we continue discussing it over coffee somewhere in the Netherlands. And let's close the session. So
yeah, thanks a lot for your questions. It's very nice.
Thank you. And I would like to remind everyone that actually this is seminar not per invitation, but you all are encouraged to submit your papers. We select the most interesting papers according to our opinion. And so it's open for everybody to present. We also try to alternate between more senior and less senior people. So in I guess in May we will have a superstar senior person. So if you want to check who it is, go to our webpage and please submit your papers. Let's close this session. Thanks everyone for participating.
Thank you. Thank you.